One of the world's greatest stories is the doubling of human life expectancy over the last 150 years. That progress has mostly been the result of the control of childhood infectious diseases. And in fact, all of us in this room are direct beneficiaries of that extraordinary progress. A child born today has an 85% chance of reaching the age of 65. 42% of those children will celebrate their 85th birthday. Many of them will go on to be more than 100 years of age. But as is so often the case, extraordinary success reveals new challenges. And in this case, we have a new and profound challenge for the continued extension of human longevity. So at the present time, we're faced with continued infectious disease problems, but the primary killer of people has shifted remarkably. We're now faced with an epidemic of age-related chronic diseases: heart disease, cancer, diabetes, Alzheimer's disease. These are the diseases that we're spending 3/4 of our investment in healthcare on. These are the challenges of the future. And let me suggest to you that new approaches are going to be required to overcome these challenges and define the next frontier in acceleration of human longevity. All great challenges need great heroes. You've heard from one of those heroes this week, Peter Diamandis, who has been a speaker with you in a number of sessions. He's a co-founder of Human Longevity. I want to introduce you to another hero. Craig Venter is arguably the most important contributor in creating a unique opportunity for all of us. And that is the beginning of understanding the software of life, our DNA code. Craig was the first person to fully sequence a bacteria 20 years ago. 15 years ago, he was the first person to sequence the full human genome. Since then, he's gone on to have other extraordinary accomplishments, including defining the microbiome. It turns out that we have more bacteria living in and on our body than we actually have human cells, and all of that genetic material is interacting with our own human cells' genetic material to impact our health. And most importantly, in 2010, Craig did something that was extraordinarily important. He created synthetic life for the first time in human history. He started at the computer, wrote the software code in the form of a DNA sequence, built the DNA material, inserted it into a membrane, and for the first time created a self-replicating form of life. Let me give you a brief review on genomics. A lot of people talk about whole genome sequencing when they're actually just talking about looking at a fragment of the whole genome. And what's possible now is to look at all 3.2 billion base pairs across the human chromosome. This is an extraordinary accomplishment, but it's not complete. And in fact, we're working very hard to look at what's called the diploid human genome, the full 6.4 billion base pairs. This will be the full characterization of the software of life. We think that this is a very important moment where a number of technologies have converged to create this unique opportunity. The first is that the cost of DNA sequencing has declined dramatically. When Craig sequenced the first full human genome in 2000, the cost to do a single genome was $100 million. It took 9 months, and it required the construction of a computer, a custom computer that at that time was the third largest in the world. Today, the cost of full human genome sequencing is down to around $1,300, and we expect that price to continue to decline. But that's not the only essential progress that's occurred in the last 15 years. The availability of reasonably priced cloud-based compute power has also made the storage and manipulation of these vast data for the first time possible. Machine learning is also a critical technology, and although this is not a new technology, it has demonstrated the potential to transform industries where rich data are available. And lastly, as a result of the epidemic of age-related chronic diseases, we are in desperate need for moving from a volume-based healthcare system to one that delivers health value and continued extension of healthy human longevity. Let me give you a brief reminder of some biology that's relevant to defining the software of life. So this is the beginning of you, and more importantly than birthdays, this is the conception day. And this is when your software is written. Basically, these two cells, these specialized cells, one from your father, one from your mother, that bring 23 chromosomes from your father in a very unique way, 23 chromosomes from your mother together, and this is the first time that your software is written and starts to work on your behalf. That cell begins to divide and creates what's known as a blastocyst. And at this point, that software starts programming all the unique cells that are necessary for the function of your body. These include your muscle cells. These include the cells that you need to see, the cells that help you feel things and think, your neurons, the cells that color your eyes, the cells that help you absorb food in your intestine. These cells and hundreds of other cells are coded for in that DNA software. And they come together in ways that are unimaginably complex to create one of these, okay? So it is this software of life that it contains all the instructions that build, operate, and reproduce our bodies. But here's the challenge. We don't know how to read that software. We've been looking at small fragments, but we actually don't know how to read the software. And that's really the next profound challenge that we think is going to provide continued progress in the single disease model for the practice of medicine that we currently have, but most importantly is also going to fuel future progress in addressing the root causes of aging so that we defer these age-related chronic diseases and we lead longer, healthier lives. So what can your genetic code predict about you? We believe the answer to this question is going to be quite surprising to people, and that your genetic code can predict much more about you than you currently believe. This is basically the game plan that we're using at Human Longevity to hack this software of life. We're building integrated health records that include the whole genome sequence, and we're combining that with extensive phenotype data. This includes environmental data, clinical data, health history. We're doing that on a cloud-based platform. We are currently one of Amazon Web Services' largest cloud customers, even though we've only done about 25,000 whole genome sequences at this point. We expose those data to machine learning at very large scale, and out of that, we believe we will gain profound insights that will drive a next generation of pharmaceuticals and medical interventions, but also the basis for a fundamentally new practice of medicine, one that begins to shift from waiting until people get sick before we intervene to acting in a fundamentally proactive preventative medicine format. How many of you have used Google Translate? Good. And I hope this translation is a good translation. Maybe you can tell me. This is an important analogy. We are embarking at Human Longevity on the translation of the language of biology in the form of sequence data into the language of health and disease. And we believe that it's so fundamentally analogous to language translation that we actually hired Franz Ock, who built Google Translate at Google, and he's currently leading our machine learning efforts. The reason we were able to compel him to take on this challenge is because we think, all of us, have the world's most important translation problem right now, and that is understanding this software of life. Let me suggest something to you that may be surprising. One of the things that we've done early on is enroll a study of about 1,000 people where we obtained three-dimensional pictures of their face to see if we could create photograph quality images of their face from the genome. And I'm happy to let you know that we can actually do this in a fairly extraordinary way, where we predict people's face from their genetic material. And this slide shows actual photographs of an individual, and then the renderings of that person that were developed, both skin tone and composition of the face, directly from the genome. This may sound like a parlor trick. I assure you that it's not. And it's a very good representation of the power of machine learning when applied to whole genome sequence data, and it will have profound implications for the way that we begin to connect medical imaging, for example, to whole genome sequencing data. We're also demonstrating our ability to identify the fundamental causes of human aging through machine learning by measuring the telomere length. These are the ends of the chromosome that begin to degrade during the aging process, that are going to allow us to compare physiologic age to chronologic age and begin to build direct medical interventions for aging, with the notion that this will prevent and defer the consequences of age-related diseases. This is a surprising finding of our early work. Both men and women begin to lose their sex chromosomes as they age. And at least in the case of men, this is associated with the risk of cancer. Again, a new target to begin to address fundamental causes of aging. We can actually predict remarkable things even from a recording of your voice. Not only your sex, but also your weight, also your height, just from the sound of your voice. And here's our first target, our first medical target for the use of these data. Right now in the United States, the risk of death between the ages of 50 to 74 years of age is 30% in men and it's 20% in women, again, largely the result of these age-related chronic diseases. We have built, for the first time, a platform that brings together at very large scale the use of whole genome sequencing, microbiome characterization, and metabolomics with traditional healthcare data, as well as advanced research-based imaging. And we're doing this to build a new way to practice medicine, one that's fundamentally data-based, preventative, and proactive. These are some of the tests that we're using. We're relying a great deal on the combination of whole genome sequencing with magnetic resonance imaging, or MRI, mostly because the quality of these images is now extraordinary, and there's no risk of radiation and no use of contrast. This is our MRI scanner at Human Longevity. These are some of the scans that we're using. Another important transition is that we're moving to quantitate all of the data that come from the MRI so that it can be used in a machine learning environment. We can now look at the precise volumes of 20 different neuroanatomical structures in the brain, compare those to normal, and follow those longitudinally. This is going to give us extraordinary diagnostic and risk prediction for diseases such as Alzheimer's, where the hippocampal volume, for example, is highly predictive, particularly in the context of genomics of diseases like Alzheimer's. We can now quantitate muscle and fat throughout the body, and this is going to give us an extraordinary new understanding of diseases like diabetes type 2, which is probably a common phenotype that results from many different pathways to what we're measuring currently as a single disease. The traditional medical record is about 3.5 gigabytes right now. The platform that we've created has taken that up to about 150 gigabytes, for the first time beginning to define the truly digital characterization of a human being in ways that we think are going to profoundly change the practice of medicine. Let me end my comments by addressing some of the policy implications of this work, and they're numerous. But there is an increasing recognition that we must begin to shift our model from a single disease focus to one that addresses basic causes for human aging, and that doing that can result in extraordinary progress, and in particular, the compression of morbidity or frailty or sickness at the end of life, as well as extending the length of life. And as you might expect, here on the left, the cost of doing this can be extraordinary. Not because individual costs go up, but because there are so many more older people as a result of these interventions. But the graph on the right shows that those increased costs can be addressed through policy changes that relate to extended work life, as well as deferment of entitlement healthcare spending. So let me end my comments by suggesting two important things to all of you. We now have the science and technology to begin to define the next frontier in human longevity. The biggest barrier to doing this is complacency, okay? Satisfaction with the status quo. And so the need, in fact, a plea from me is for leadership. To get us to this next frontier, and for all of us to collectively benefit the way we have from control of infectious diseases, leadership is required, and all of you have an extraordinary opportunity to positively impact the lives of billions of people that live in this region. So let me welcome you to the next frontier of health and medicine. Thanks very much.